Good morning, everyone. It's an absolute pleasure for me to give this keynote presentation. And at the outset, I would like to thank the Sri Lankan Geotechnical Society and the organizers of this conference, ICGE Colombo, for inviting me to give this keynote lecture. I would like to acknowledge the contributions from my co-authors, Dr. Trung No, Dr. Yu-Ji Kee, and Professor Cholachat Rujikiat Kamjong. My presentation will include two parts. Firstly, I will talk about soft soil improvement for road and rail embankments with applications of vertical drains and vacuum pressure. Part two will be quite different in terms of sustainable design solutions, where I would look at the use of recycled waste materials for improving road and rail infrastructure. Coming to part A, looking at soft soil improvement with vertical drains and vacuum preloading. On the left-hand upper picture, you will see a vertical drain installer with the steel mandrel that is in this system here. And the vertical drains will be installed through the steel mandrel into the pre-desired depth into the soft soil. And here on the right-hand side, you can see that on top of a sand platform on which this PVD installer can travel on, circular vertical drains have been installed at a regular pattern. In this particular case, it looked like a square pattern. And these drains have been installed to that pre-desired depth. On the bottom pictures, you will see the installation of the membrane, the impervious membrane that you can see here. And the periphery of this membrane have to be buried in a trench and usually backfilled with something like a bentonite slurry, just to make sure that you get a complete tight seal, as you can see from this middle picture here. Then the hoses for vacuum preloading have to be put in underneath this membrane and then connected to the vacuum pump. And when the vacuum pump is switched on, then the vacuum pressure will be applied and propagated down the vertical drains to the pre-desired depth in the soft ground. Just to explain the principle of vacuum consolidation, in this plot here on the left-hand side is the application of surcharge pressure just with the embankment fill only, without any vacuum preloading. So it's got the vertical drains with the embankment fill. Now, if you start with the excess pore water pressure diagram, then at the start, immediately, the excess pore water pressure will be the same as the preloading pressure, which in this case is 100 kPa. And then the pore pressure will start to dissipate with time from 100 kPa towards zero. But if you were to apply 50% of that total stress with vacuum preloading, so that the total pressure is 50 kPa, and the vacuum pressure is minus 50 kPa, so that the total stress is still 50 minus 50, that gives you 100 kPa. The difference, of course, is that the excess pore water pressure will start with 50 kPa instead of 100 here, but then it will dissipate towards minus 50. So between these two systems, the difference is mainly with the excess pore water pressure distribution, and therefore the excess pore water pressure at any given time is not going to be the same in these two systems. However, the effective stress, which is calculated by the total stress minus the pore pressure, will be exactly the same in both systems, and therefore the ultimate settlement will be exactly the same whether you have the vacuum pressure or not, as long as the total pressure is exactly the same. So the radial consolidation equation is given here, which is the inhomogeneous Laplace equation. And you can solve this equation by transforming this diagrammatic picture into an equation where you can, with time, calculate what the vacuum preloading pressure is as a given time, as you can see from this suction line here. So assuming that the degree of consolidation is exactly based on the rate of pore pressure dissipation, as for the solution of this equation, then the degree of consolidation can be calculated with this equation, which I have proposed in 2008, and the denominator of the equation will give you the vacuum pressure. Now, please note that the vacuum pressure, I have used the modulus here, that is the positive value, because essentially your vacuum pressure is a suction and therefore negative. So in this case, the value that you use in the equation is plus 50. And then you can calculate the degree of consolidation. Looking at the application, this is the Port of Brisbane ground improvement, a project that I was involved in for quite some time over the years. And a lot of research has been done using the Port of Brisbane data. Now, you can see here a barge that is dredging the oceanic mud and the dredged mud and the sands, and then pumping it to the area where you need to reclaim that land. And then this dredged mud has to settle, and then the sand platform has to be put in. And then once the sand platform is there, the vertical drain installer can conveniently travel on it, installing these vertical drains, as you can see here, for a given pattern. You can see the barge in the background here. So it's really the same project area. That is a completed picture here of the vacuum preloading site. You can see the impervious membrane that you can see the black color here, like an L shape, and that is along the marine boundary. But away from the vacuum preloading area is the sites where a surcharge load only has been applied to consolidate the ground. Now, it is important at this point that I explained to you that there was a specific requirement in this project that along the marine boundary, that there was a requirement that there should not be excessive turbidity of the water because of the soil being laterally moved into the water. And as a result, in order to control this lateral movement, obviously, the best solution was to apply the vacuum preloading, because vacuum preloading will decrease the lateral movement because of the isotropic compression that is inwards in terms when you apply the vacuum pressure. I will explain this a little bit later, but to repeat that, the most important aspect is that vacuum preloading can control effectively the outward lateral movement. So here is the area that required development in Port of Brisbane. And here is an interesting picture that the machinery cannot simply travel or even rest on materials, very soft materials that has not been consolidated and strengthened. So this is dredged mud where the bearing capacity is extremely weak, and as a result you can get significant damage to equipment like this if you are not careful. Now here is a site, the site where you can see the vacuum preloading as highlighted in yellow, and away from that marine boundary here, then you had the sites where the consolidation of the ground is only made by surcharge fill. The soil properties are given in the right-hand bottom picture. You can see that the water content of the upper Holocene clay, approximately say 5 to 10 meters below the surface, the water content is very close to the liquid limit. In other words, the soil exists in that depth, almost like a slurry. So extremely soft, in other words. If you were to look at the CV and the CH values, the compressibility coefficients, they are typically around 2 to 4 square meters per year. And then the undrained shear strengths are less than 20 to 30 kPa, typical of extremely soft soils that require significant improvement before you can place infrastructure on top of that. So here is a summary of the construction history, the settlement curves for various sites, including vacuum preloading sites, VC1 and VC2, and the remaining sites are surcharge only, and these are constructed at different rates to different heights, and therefore the rate of settlement is expected to be different, as you can see from these various pictures. But something significant that you can observe is where you look at the excess pore water pressure. Normally you will find that when you apply a vacuum pressure, you get isotropic consolidation inwards, and as a result, the rate of pore pressure dissipation with vacuum preloading tend to be greater than the rate of pore pressure dissipation with the surcharge fill alone. And that is why you will get accelerated consolidation when you have both surcharge fill and vacuum preloading in conjunction. In addition to that, as I explained earlier, that vacuum preloading has the collateral advantage of significantly decreasing the lateral movement. As you can see from this figure here, as you apply the vacuum pressure, the lateral movements are decreased significantly, as you can see from this red arrow, to marginal value, so that the ground not only consolidates to a higher shear strength, but also the ground is subject to less lateral movement, therefore greater stability. Now I'm coming to the situation where the water content and the liquid limit is very close to each other in the subgrade naturally, like a floodplain. Right? Even in Sri Lanka, you get floodplains where the water content is sometimes greater than the liquid limit. And you can have this in very soft estuarian clays. You can have this situation in black soils like peats. And it is important that these soils are treated in slightly different way. Because unlike static loads, when you apply a dynamic load, like a heavy haul train railways, then this soil can actually fluidize because the water content is very close to or equal to the liquid limit. And if I can run this picture here, this is a distinct element analysis coupled with computational fluid dynamics or CFD-DEM coupling. And you can see that when you apply this differential pressure, the hydraulic gradient, the soil will fluidize and pump upwards. But this value of delta P is not large enough for this material to come to the top of the railway track in this particular case. That is the ballast that is simulated with spherical particles. Now, if I were to run this second picture, the value of this pore pressure differentials is much higher, about 2.5 times greater than that. You will find that that is adequate for the fluidized soil to be pumped to the top and then completely pollute that ballast, as you can see from this right-hand side picture here, which is a typical case of mud pumping in an Australian railway line in the state of New South Wales. So under these circumstances, these tracks cannot be operated because drainage is completely impeded, and also the bearing capacity of the track is significantly compromised because of this mud pumping, and the track needs to be cleaned up and repaired before the trains can operate again. Now, how do we prevent this mud pumping phenomena, which can be catastrophic in the event that a train derails? And just imagine a passenger rail suddenly going on a track like this, and suddenly you're going on a sponge and the train derailing because there is no bearing capacity on the track. Now, in order to dissipate the excess pore pressure and to prevent excessive hydraulic gradients, one way to alleviate this risk of subgrade mud pumping is to install vertical drains. As you can see from this triaxial sample, where the soft soil is stabilized with a vertical drain in the middle and then subjected to cyclic loading, mimicking a typical heavy haul train. So the cyclic stress ratio that is given here is defined as the cyclic deviator stress divided by 2 times the confining pressure. So in typical heavy haul trains, you will find the CSR value to exceeds around 0.3 and may go up to about 0.6. So if you do not have vertical drains in such a soil where the water content is close to the liquid limit, then you get the risk of maximum pore pressure, the mean excess pore pressure rapidly increasing, therefore making the effective stress going to practically zero. The soil will fluidize and the track will fail. But however, if you have vertical drains like this, then the excess pore water pressure will not increase rapidly. In fact, the excess pore pressure will dissipate and arrive as a relatively constant value. So in the event of a very small value of cyclic stress ratio, like say 0.2, even without PVD, maybe the soil will tend to become unstable, but then achieve stability after a certain number of cycles. So you have to hit a balance between how much stabilization you need with vertical drains compared to the possibility of this mud pumping, as you can see very well from this picture. So this can be applied to real life scenarios. So this is a picture that is taken from Sandgate, a town north of New South Wales, and you can see severe flooding of railway tracks. And under these circumstances, the water content of the subgrade soil will be very high. And just imagine the railways operating after these flood waters have receded, but the water content of the subgrade soil will be very high and the water table will be high. So vertical drains will need to be installed into this kind of soil to make sure that railways in this particular area can be stabilized with vertical drains. So I was asked to make this Class A prediction before the track was actually constructed. So here is the prediction of the railway settlement, the track settlement with time. And this is using the vertical drains. And then once the field data was available, approximately 1.5 years after my predictions, these data has been plotted here. And you can see that the settlement predictions are very acceptable and they are quite close to the predicted value. If you were to look at the excess pore water pressure development in this particular case, if we had not used PVDs, then the excess pore pressures would have been pretty high. But with the use of the PVDs, the excess pore pressures have dissipated substantially, and you can see the rate of pore pressure dissipation coming towards zero, and after about 1 year, the excess pore pressures are insignificant. Same thing with lateral movement. If we did not have the vertical drains, the lateral movement would have been significant, close to the surface, about 45 millimeters of movement. But with the PVDs at 1.5 meter spacing, the lateral displacement could be decreased substantially to about 35 millimeters. And you can see the field data after about 1.5 years for the same track. They are very close to the predictions of the PVDs that I had made earlier. So this is a typical application of how vertical drains can stabilize very soft soils, especially under high water content, and prevent the phenomenon of mud pumping. Now, there is another way that you can prevent mud pumping in railway tracks in particular. That is the use of geocells. Now, those of you who are not familiar with geocells, you can consider them as membranes in 3 dimensions. And these pockets can be filled with all kinds of granular materials, including waste materials, crushed rock. And then this material with the geocells can be placed as a capping layer before you put the ballast, railway ballast, on the track. So in fact, what this infilled geocell layer offers is to prevent the downward propagation of the stress into the very soft subgrade. So in this 3-dimensional finite element model, the geocells have a confined capping layer. That layer here is on the shallow part of the track, just underneath the ballast here. So the ballast is just here, then the capping layer is here, and then the unreinforced soft soil is underneath that. So when I run this program, please note that when you see the red color, that means the lateral movements are too high. Whereas where you have the geocells, they confine the material very well. So the lateral movements in this area should be relatively low, and you should see the blue or the green color. So let's run this. As you can see, where the soft soil is unreinforced, the lateral movements are very large, but where the geocells were, you can see that the lateral movement are relatively low, and therefore the track is significantly stable because of the geocells. So that's an application of geocells to prevent mud pumping. Now with that, I'm coming to part B on the sustainable design solutions using recycled waste materials. Now, all of you know that large amount of rubber tires are discarded annually, almost in every country, and Sri Lanka is no exception. In Australia, we discard nearly 1.5 to 2 times the population of tires every year outside, just from cars and commercial vehicles and also mining machinery as well. And this is a picture of one of the world's largest spoil tips that are used for rubber tires. You can see millions and millions of rubber tires piled up from all kinds of Middle Eastern countries that are brought here and put onto the spoil tip. But these tires can have contaminants, they can have petroleum contaminants, and occasionally they can catch fire, as you can see like this. It's an extreme disaster with so much toxic gases being emitted to the atmosphere, as you can see. In Australia, about 97% of the tires are just put into spoil tips or landfill, and very little is actually recycled for good purposes. So this is the importance of my presentation in this part B. So how can we use these recycled materials? So one good example is these recycled rubber tires can be made into rubber sheets. And these rubber sheets can be put under the ballast in railway track so that these rubber sheets can absorb energy during the passage of railways, during the passage of trains. So the kinetic energy of the moving trains can then be transformed as strain energy into these mats. And when these mats absorb this energy, that prevents the energy dissipated into the ballast and the other railway components, therefore protecting them for damage and deformation. Then the rubber tires themselves can be assembled together and infilled with granular materials, including waste materials, and then tested to ensure that they can provide a good capping layer. So this is a little bit like the geocells that I explained earlier. In geocells, you fill the geocells with granular material and put them below ballast. Now replace the geocells with waste rubber tires. You got plenty of them, and they can be used and infilled, and then the railway track can be built on top of that. And the materials that can go into this as infill materials can be coal wash coming from coal mining industry, steel furnace slag coming from steel industry, and these waste materials can be mixed together with rubber crumbs as an energy absorbing material and then infill these tires. There are many publications in this area coming through, and you can refer to these publications as you can see here. So this is a typical application in the extension of the Port Kembla harbour in Australia, close to the city of Wollongong. And I was involved in this project. And you can see that coal wash and steel slag is brought to the site of this Port Kembla. And you can see the black color coal wash, the light gray color steel furnace slag, and then they are mixed together on site and then spread into the area that needs to be reclaimed and then compacted with an intelligent compactor. And intelligent compactors are becoming very popular these days because these compactors, when they are compacting the ground, they can actually calculate the stiffness during their travel and then decide how many passes are required back and forth in order to achieve a pre-desired stiffness of the compacted ground. So one of these applications is to use a seal or a synthetic energy absorbing layer just below the ballast. So replacing the top sub-ballast with this waste material. So that's coal wash here, that is steel furnace slag, and that's rubber crumbs. That is rubber tires. You can crumb them into little shreds or crumbs and then mix them together to make an energy absorbing material. If you want to make this energy absorbing material ductile, then you can just mix the coal wash with rubber crumbs and you get a very ductile material. If you want a material that needs a high bearing capacity and also extremely stiff in order to minimize the settlement of the railway track, then you can mix with a larger proportion of steel furnace slag, which is very strong and hard, and then you end up with a seal mix, which is relatively stiff. But the problem with this stiff mix is that it can be brittle and under cyclic load is prone to cracking, whereas the more ductile mix, you don't get cracking, unlike this mix here. So this is what I've just mentioned. So if you look at the stress strain curves, a material which is brittle will have a high peak shear strength, but then the post peak shear strength drop will be substantial, as you can see from here. But when you increase the rubber content from 0 to 15%, you will see that the curves are becoming more ductile. But of course, there's a slight compromise of the shear strength drop from this value to a slightly lower value. So if the shear strength and the bearing capacity can be reduced a little bit, very often you'll find that a ductile material is more long lasting and better for a railway track than a highly brittle material, even if that material might have a higher bearing strength. Now, the other advantage of having the rubber crumbs is that you convert the material from a dilating material to compressive material. So more rubber that you have in a mix, the more compressible the material get, and therefore you can achieve the shakedown condition under cyclic loading a lot more quickly than a material that typically dilates and make the track unstable. More information of this you can find in my paper in ACE Journal of Geotechnical and Geoenvironmental Engineering in 2018. So these materials can then be tested in large-scale experimental work in one-to-one testing. This is a cubical triaxial equipment where the typical track elements such as this with sleeper, ballast, the seal, and the structural field can be set up and loaded under cyclic loading. So that is your cyclic loading. And then you can, with the instrumentation that is placed inside this box, you can actually measure the deformation and the degradation characteristics of the material. So something here is a very important summary of testing of this material. This is a material where steel furnace slag, coal wash, and rubber crumbs are tested together in this large-scale cubical triaxial equipment, and the results have been published in the journal Geotechnique with Dr. Yu-Ji Ki, who's one of the co-authors, and this is following up her PhD work and postdoctoral work. Now here, at very low values of deviator stresses, irrespective of the rubber crumbs content, the materials will achieve a stable state. In other words, the axial strain will increase and then become constant and then will not change anymore. We consider this stage as the plastic shakedown, where when the material achieves a plastic shakedown, there is no further volumetric strain, as you can see from here. Now, if you were to increase that deviator stress to much higher values, so that the loading of the trains or the length of the train or the weight of the train is now higher, then you will find where the rubber content is significantly higher than 20%, then you will not get this shakedown condition. The plastic axial strains will continue to increase like this. But where you have the lower values of rubber crumbs, they will still achieve the plastic shakedown conditions. Whereas in range B, where the axial strain continue to increase, we can consider that as equivalent to plastic creep. If you were to increase the deviator stress even more, then the range that you have for large rubber content is that the axial strain will not even achieve plastic creep. In fact, they will go to incremental collapse, like this as you see from range C. You cannot see this very clearly with these values here, but if you were to increase that Qmax to say over 200 kPa, will you get the stress strain curves that looks like that. So ideally in a railway track, you need to be between range A and range B in order to keep the track stable. So the three most important conditions are the plastic shakedown, plastic creep, and incremental collapse. And we have to avoid this range B to range C if you are working in a railway track using these waste materials. So if I were to put this into a design chart that can be used by practicing engineers, you can see the plastic axial strain plotted in the vertical axis, the cyclic deviator stress given in this horizontal axis, and the rubber content is given in this second horizontal axis. So when you are in the left-hand lower corner, you are in range B, range A, where the axial strains are small, the cyclic loading, cyclic deviator stress is relatively small, and your rubber content is between say 0 to 15%. As you go up to the right, then you get the range B, which is creep, and when you go to the top, you have high rubber content and then high plastic strain rates, and of course the deviator stress has to be much larger than 100 kPa if you are in this range, and that is the incremental collapse. So in order to design infrastructure well in design, whether they are roads or railways subject to cyclic stresses, you need to be in that range between range A and range B. Coming to the use of rubber sheets, now this is just a picture illustrating how rubber tires can be converted to these rubber sheets, and then they can be put underneath the ballast, such as this schematic diagram here in a railway track, and you can see the picture of a real track in the town of Singleton, where these recycled rubber mats are being used before the railway ballast is compacted on top of that. So the testing of this material is done in a modern, iconic triaxial test, cubical triaxial test, where the loading is in 3 dimensions, and this dynamic actuator can apply to simulate the heavy haul train loading very accurately. And you can see the actuators on the horizontal side that can actually monitor the lateral displacements and the lateral strains. So here is a picture of application of these recycled rubber mats. So these are the recycled rubber mats now placed on a concrete bridge deck. This is the picture at the right-hand bottom, and this is in the town of Singleton. In the same track, where you don't have a bridge deck, you have the normal ground, there is no recycled sheets being used, but instead you have a geogrid, plastic geogrid, conventional geogrid being used to prevent the particle movement. So this is the conventional form of railway tracks with geogrids, and this is a typical case where you use rubber sheets. Now rubber sheets become very useful where the particle breakage, like the ballast breakage, is maximum. And you can imagine that particles break more when the subgrade is stiffer. So if the railway track is built on rock, or whether it is based on concrete bridge deck, then the particle breakage is more compared to a track that is actually built on a soil. So these two pictures here show the pressure cells being placed on that same bridge deck here, so that you can monitor the pressure that is transferred to this bridge deck. And then here in this picture, you can see the settlement points and also the horizontal transducers that actually measure the lateral movements of the particles. So this is a summary of comparing the geogrids with the recycled rubber mats used in this particular project. Now, as I said earlier, on concrete bridge decks, the particle breakage is significant. Here you have a ballast breakage index greater than 0.15 or 15%. That's a higher value here. So if the railway track is made of rock, the subgrade is rock and the track is built on this subgrade rock, then the ballast breakage index can also be very large, over 0.12. And if you use a geogrid on this particular rock track, then you can reduce the breakage to that level there. As I said earlier, if the railway track is built on a soil subgrade, then of course the breakage is much less to start with. And if you have a geogrid, the breakage reduction is even more, as you can see from this curve. The last curve here is the breakage on a bridge deck. Now, if you did not have a recycled rubber mat, then the breakage is right at the top of this curve here. And then with the laying of the energy absorbing rubber mats, you decrease the breakage all the way down from about 0.15 to something around 0.04, a significant reduction. So my conclusion here is that while the conventional plastic geogrids are very good at reducing the lateral movement, they are not designed to prevent particle breakage, although there is some reduction in the particle breakage that is being achieved. But if you want to reduce the particle breakage actively and increase the longevity of the lifespan of a railway track, then you need to use these rubber mats as energy absorbing material in order to reduce the particle breakage, as you can see from this bridge deck example here. Now, how do we use these rubber tires to make a capping layer, such as the one that I showed with geocells? So these are discarded car rubber tires, all put together on a floodplain where the water content of the subgrade soil is very soft clay, and this is in the town of Ballast. And you can see that these rubber tires are then infilled with granular materials like waste rock. Even the discarded ballast from previous railway tracks can be brought back and used as an infill material on these rubber tires, which are put together and then compacted. Then you get this very strong capping layer. And the advantage of this capping layer is that because of the confinement provided by these rubber tires, materials can't go anywhere with this confinement. Then you have a very resilient capping layer with very little lateral movement, and ideal as a capping layer to build a railway track. So this is one of my PhD students, Fatima Mahmood, working with this concept. And this is an international patent pending with this application. And she is looking at using this capping of the structural field. And on top of the structural field, rubber tires are assembled. Each rubber tire is instrumented like this with sensors. So you can see the pressure distribution around the rubber tire, as well as the displacements and the forces, contact forces between each rubber tires. All this is measured during this experiment. And then they are assembled and then tested by the high-speed rail testing facility that we have under the Australian Research Council. So you can see that massive equipment where this is mimicking the loads and the speeds of the actual trains that are applied by these actuators. Just to give you an idea, each of these actuators is about 1.2 meters high, and there are 4 of them working in pairs. And as a result, they can mimic the moving load of these trains and the speed of the movement of the actuators, and the loading magnitudes can be controlled by the computer system that is on the side of the facility. This can be done, simulated also with finite element method. You can see a typical embankment, railway embankment with the rubber energy absorbing layer, which are these tires all put underneath that. And then these finite element methods such as abacus or plaxis can be applied, and you can see the rubber tires here just underneath the embankment. And then you can do the analysis of using the finite element method. And as you can see that when you have the confining capping layer for this rubber with these rubber tires, the lateral movement of the railway track can be dramatically curtailed to about half the original value. So in this particular case, if you had a conventional railway track, then the lateral displacement maximum just underneath the ballast would have been about 35 millimeters on top of the subgrade. But with the capping layer, you reduce that to about half that value. So it's a considerable reduction of the lateral movement and increased stability of the railway track. More details of this finite element analysis, for those who are interested, can refer to this publication in 2017 in Transportation Geotechniques. So 2 most important aspects that I would like to bring to your notice. With the rubber tire assembly, 2 key contributions are provided. One is that you decrease the lateral displacement at any given time. The horizontal axis here is the number of cycles, and the lateral displacement is plotted in the vertical axis. And as you can see, when you have the rubber tires, the lateral displacement are decreased substantially from the track that does not have these rubber tires. At the same time, because these rubber tires are infilled and you prevent the lateral movement of the material, the resilient modulus and the shear modulus of this capping layer is increased significantly. So you can see that the railway track now has a larger modulus. And the advantage of having a larger modulus is, of course, you decrease the settlement of the track. So if the settlement of the track is something that you need to control, then it's a very good idea to use a rubber tire infilled capping layer, as I have illustrated in the previous pictures. So to come into my conclusions, the PVD and vacuum preloading system is very effective in accelerating the consolidation, gaining substantial increase in the undrained shear strength. Apart from that, you can reduce the lateral movement of the soft soil. And this is particularly important if you are dealing with a marine boundary, like a reclamation area, where you need to cut down the lateral displacement to prevent the turbidity of the seawater. The synthetic energy absorbing layers, including the recycled rubber mats, are very useful to prevent the breakage of the granular materials such as ballast, and also to reduce the track settlement. And in my view, they do a better job than plastic geogrids, where you have to reduce the ballast breakage. Infill rubber tire layer is very attractive because that is one way of getting rid of waste tires in a very useful manner. And also the infill material that goes into these rubber tires can also be a waste material, a granular material that can be compacted. So in other words, the waste that is generated by industry and automotive industry can be put as a very important aspect of the railway substructure to prevent lateral deformation and breakage by increasing the confining pressure of the track. The finite element models and distinct element models that I shown earlier are very useful to predict whether your soil can mud pump or fail in undrained instability, or whether the settlements can be too much. And these numerical models can now be used in conjunction with conventional design. Once the tracks are built, please don't forget to monitor them. So field instrumentation is very useful to make sure that your design does the work as you initially predicted or desired by performance validation through full instrumentation. I would like to finish my presentation by acknowledging the Australian Research Council that has supported my research for the last 2.5 decades, the Transport Research Centre at the University of Technology, Sydney, that has provided a lot of support for this ground improvement research, past and present PhD and master students, research associates and technical staff whose contributions have been invaluable to this kind of research that we have done. And finally, but last but not least, the industry that owns infrastructure. As you know, universities do not own infrastructure in the field, the industry does, but they have been able to take these research outcomes, adopt them in practice, and benefit immensely by transforming the conventional design practices. And I thank this industry significantly for helping us with linkage research practices. Now, if you have missed any of those important aspects in my presentation, I will kindly ask you to refer to 2 of my recent books on railway technologies, and they will have all these described in greater details. And if you want more details on PVDs and vacuum preloading, you can refer to my books on ground improvement that will discuss them in detail. And this is a picture where all this research has been adopted by industry and put into practice in the Chullora suburb of Sydney, thanks to Sydney Trains that own all this area. So you can see this area, Chullora, where all these things I talked about, rubber tires, rubber sheets, and so on, they're all being put into this area for real trains to benefit from these methodologies. Thank you very much.